Hi, I'm Kanchan Ramsingha, and today I'll be presenting our work on orthogonal projection loss. In this paper, we propose a novel loss function, namely orthogonal projection loss, or OPL for short. And here we basically apply constraints on the feature space in order to A, cluster same class features together, and B, to separate different class features apart. Note that the features learned by OPL are more discriminative and generalizable. By discriminative, we mean how well a set of features performs on tasks over examples that are from the same distribution as the trained distribution, and this can be evaluated using vision tasks like standard classification. And by generalizable, we mean how well a set of features performs on examples from distributions outside the trained distribution. This is measured by tasks like few-shot classification, domain generalization, label noise, and adversarial robustness. We note that OPL improves over a selected simple baseline across all these tasks. We now explore OPL in detail. OPL is applied on samples within a mini-batch, where we first select all pairs of samples, and then these pairs are separated into same class sample pairs and different class sample pairs. And the same class samples are pushed together while the different class sample pairs are pushed apart. And we hypothesize that this separation and clustering carried out simultaneously would improve both the discriminativity and generalizability of learned representations. Moving on, the exact implementation is done using a cosine similarity operator on these two sets of samples, where the term S includes all same class samples and the term D involves all different class samples. And the cosine similarity operator adds an orthogonality constraint on the different class samples when we try to minimize this D term, and it pushes all the same class samples together when we try to increase or maximize the S term. And OPL is simply a linear weighted average of these two terms. And OPL is directly used in line with cross entropy loss. And as explained in the diagram, OPL increases interclass separation while improving intraclass clustering. We now explore the reasoning behind the orthogonality constraints. Firstly, given the generally used random mini-batch based training setting, we note how under this orthogonality constraints provide a more definitive optimal in relation to other methods like max margin separation. And this in turn leads to more stable training, especially when working with smaller batch sizes. And furthermore, we know that orthogonal projection loss avoids unnecessary negative correlation constraints in comparison to max margin methods. Finally, we explore training with OPL. OPL has a very efficient and straightforward vectorized implementation, which means it can easily be plugged in over any method that is currently using cross entropy loss. And furthermore, OPL achieves the expected objective of separating and clustering classes or class samples in feature space. This is visible in the two graphs where the cosine similarity of same class samples reaches 1 and that of different class samples reaches 0 during training. Finally, we provide some detailed evaluations, firstly on ImageNet, where classification accuracy is reported, and then on adversarial attacks, few-shot learning, and also some more on few-shot learning, label noise, and domain generalization. Finally, our code is available publicly. Do visit our project page and have a look. Thank you.